Good evening once again. Today we'll be looking at t-tests. Though the slide that you are seeing contain information about t-tests and the non-parametric counterpart of t-tests. But what we're going to look at today is a t-test. So you see something like comparison of two means. You know, you use t-test to compare two means. That is, there must be two means you're comparing. And in a situation where you cannot use t-test, any of the three t-tests, you can use non-parametric. So you cannot use any of the t-tests because maybe not all the conditions for, or the most important condition for using parametric tests are not met. So you now use non-parametric counterpart. Okay, now we discuss t-tests. We first of all discuss t-distribution. Then we'll talk about t-tests. Now, let's just have some historical background. You can see a picture of somebody. In 1908, William Seeley Gosset was an Englishman publishing under the pseudonym Student, developed the t-test and t-distribution. Gosset worked at the Guinness Brewery in Dublin. He found that existing statistical techniques using large samples were not useful for the small sample size that he encountered in his work. So this man was working in Guinness, and by that time, you know, it was in the data session. So you cannot publish using their data without their permission. They're working in the company, reputable company like and powerful multinational company like Guinness. So instead of, because if he has published using his name, they will be quoting Gosset, and they will know that where did he go out to collect data from? They will know that their company data was using to fly. So he was now using the name Student. He found out that by that time, they were using normal distribution, Z-test. You know, I've already talked about Z distribution, that is standard deviation. So they were using Z distribution, that's standard normal distribution, to compare means, two means by that time. But he discovered that some of the data he got are not so many, sometimes less than 30. The group of data will less than 30 what he wanted to compare. So if he knew that, he realized that they were too small using normal distribution or Z-test to compare them. So he developed this, or is it developed or discovered t-distribution and invented t-test. Student t-distribution, simply t-distribution. Sampling distribution of the t value when the sample consists of independent, identically distributed observation from a normally distributed population. So though it's from normal distribution, what we are saying that the attributes under study are normally, if there is no outlier, they should be normally distributed. But the issue is the sample size. So samples are very small. So family of continuous probability distribution with degree of freedom n-1. So you know we have talked about continuous probability distribution. There is a type of distribution in which you cannot know all the value, you cannot know the probability of all possible values. And we see the most important among them is normal distribution. So chi-square distribution is one of them. T-distribution we are discussing is one of them. F-distribution, one of them. So it's a continuous probability distribution. As the number of degree of freedom increases, the t-distribution approaches the normal distribution. Just like chi-square, as the number of degree of freedom increases, it approaches normal distribution. It's the same thing with t-distribution. At the level of degree of freedom, you know that in this sense, especially for T distribution. The number of degree of freedom and the degree of freedom vary directly with sample size. There is not the same thing with chi-square. The number of degree of freedom in chi-square vary based on the number of cells because you use cross tabulation for that one. Number of cells in the common number of category. Let's say number of category. Because if you say I think it's better number of category of the outcome and exposure. Number of the category of the variable you are dealing with. You know, of course, the chi-square is for categorical variable. So number of category is what they, because when you are comparing two variables, looking at association between two variables in using chi-square, you know that when you use cross tabulation, the number of cells will not depend on the number of the category of each of them. So now we're back to T distribution. So this one directly is the sample size that determines the degree of freedom. Used for estimating the means of normally distributed population in situations where sample size is small and the population standard deviation is known. So that is, you can also use it if you don't know, even if the sample size is not small, if you don't know the standard deviation of the population. So let's talk more about it. The probability density function is symmetry. I've already told you the graph of continuous probability distribution. The graph of any probability distribution is called probability density function. So like now that normal curve is probability density function. This one we are looking at is probability density function. The chi-square distribution we saw the graph, they are all probability density. So the probability density function is symmetrical, just like normal distribution. No, mean, mode, and median the same. You can see it's only that the degree of freedom. Can you see? You see the shape. The red one is normal distribution. The T distribution, you see that what is flatter. You will be surprised that the area under the graph is the same for both of them. So, but for normal, you see the red is normal distribution, see the blue is T distribution. Its overall shape resembles that of a bell shape of a normal distributed variable, which means 0 and variance 1, except that it's a bit lower and wider, as you can see. Look at it. We want to also look at z-test versus p-test. But on this graph you are seeing now, it's trying to show you how the degree of freedom vary with sample size, or let's say how the shape of the T distribution vary with sample. So different shape, different degree of freedom. So in this one, the one when you see red is showing the normal distribution. In this second right upper graph, you see. Come here. No, it's not normal distribution. It's just showing the one with degree of freedom of 10. So what this was just showing that different color just showing the degree of freedom is very, as the degree of freedom increases, it's becoming taller, like normal distribution. That one that is infinity, you see standard normal distribution, that black one is a standard normal distribution. But when the degree of freedom is above certain level, that's why I say with infinity degree of freedom, once the degree of freedom is above 30, the T distribution look like normal distribution. It approximated. So look at the one to the lower right side, you see Z distribution, the blue, you see T distribution with degree of freedom of 30. Then we have T distribution with degree of freedom less than 30. The other one close to 30, red close to 30, the green less than 30. So close to the once it reaches that 30 now, it become like normal distribution. So all this guy just showing you how the value varies and as it approaches normal distribution. Look at this graph to the left lower quadrant. You will see the at 95% confidence interval. At least, if you remember, we talk about 95% confidence interval. You can see the Z distribution is the one in blue. You can see it. You can see the T distribution. It's shown 95% is 2.2. T is 2.201. Can you see? That is the T of degree of freedom 11. That is, N is 12. Sample size is 12. Can you see now? Because you know the graph is wider. So as the graph is shrinking back, narrowing back, becoming taller, it approximates that of normal distribution. So just for you to have a pictorial view of the way it look like. And the same thing, the critical value, because when you calculate the t-test now, the t-value, how do you know that it has reached a particular value? How do you know? Let me go back to this thing. You remember? How will you know that that thing has reached a critical value? That critical value is when the middle 95% of the graph is. That is the critical value. For T of N is equal to 12, you can see it's 2.201. We all know for the Z distribution is 1.96. That's what is showing there. So the same thing, you come here, you look at the degree of freedom and confidence level. There's something I just remember now. We have discussed introduction to inferential statistics where I talk about p-value, and I told you level of significance. The level of significance and confidence level, they are complementary. They add up to 100. So if your level of confidence, I think I said it, is 95, the level of significance will be 5%. 95, 5%. If the level of significance is 1%, which is 0.01, then the level of confidence is 99. Can you see now? So it's 99%. So the level of significance and confidence level add up to 100. So that's what you see. If you even look at it when I was showing you the T table, you will see the same thing. When you see 95, you will see the remaining 5%. The remaining 5% may be, if it is, though they will show where is it 1T or 2T. If it is 1T, the remaining 5% will be on one side. If it is 2T, it will be on both sides. That 5% divided to 2.5, 2.5. So at 95 now 2T, you look at the degree of freedom to know the critical value. If you look at around that 30 degree of freedom, 30, you see something like 1 point with the 95. Look at that third to the last column. That's what corresponds with 95 confidence level, 0.05. Look at that column and match it with degree of freedom 30. You see okay. 30 or 29, you see the value there. The thing is not clear, I'm seeing. Okay, 30, degree of freedom, 30. You see 90%, 95%, but we'll come to it later. Now, let's now look at Z-test versus T-test. Why is it? Some people will try, why don't we use Z-test to compare two means? Why do you use T-test? Now, there are reasons for choosing whether Z-test or T-test. But those reasons, if you look at it very well, there's no point using Z-test. You use T-test. You see? Generally, Z-tests are used when we have large sample size, greater than 30. T-tests are most useful with a smaller sample size, less than 30. So both methods are normal distribution of the, assume rather, the normal distribution of the data, but the Z-tests are most useful when the standard deviation is known. But let's look at the algorithm here. Look at it, say, do you know population standard deviation? Suppose it's standard deviation. You say yes, you go. If you say no, do T-test. So because if you don't know population standard deviation, you cannot use Z-test. You have to bounce on T-test. Now, even when you know population standard deviation, is the sample size above 30? Yes or no? If yes, you use Z-test. If no, you use T-test. You can see out of the two stations now, you see, or is it 3 options? Because if you look at the options, you discover that you are likely to use T-test. Now, funny thing, they say if you, the last one, I say sample size greater than 30. So the sample size has to be greater than 30 for you to use Z-test. But the issue there is that at 30, the T-test approximates Z-test. So the T-test is like, it's very close. So at that, even you can use T-test. So that's why you see, you won't see any statistical package comparing two means you are using T-test, because it's for whichever situation. From the time Gosset discovered T-distribution and invented that T-test, has taken over to compare two means. Now, we remember when I was giving introduction to, when we were talking about assumption around hypothesis test. This is the formula T-test I used to demonstrate. I say that it's simpler to give you clue. So T-test statistics down, test statistics, observed value minus hypothesized value over standard error of observed value. I already said hypothesized value is the same thing we call expected value. When you say expected value, it means hypothesized value. But the meaning of hypothesized value is that the value when null hypothesis is true, when there's no difference between the group you are comparing, when there's no difference, no association between the two variables. What is the expected? What's the difference? That is the hypothesized value. So we already said that if it's the same, if you say the mean age of group or the mean weight of two groups is the same, it means that if you remove one from there, it gives you 0. That's why that mu minus mu1 minus mu2 will be 0. When you look at the second formula now, you now see that that one is out of it. So the t-test is by x1 minus by x2 over standard error of both group. Now, actually, this one you just formula for independent t-test. Talk about it later because the other two peer t-tests, one sample t-test, we'll go through it. But before, just to remind you, though we have discussed this, more like repetition, under the assumption around opposite test. Condition for using parametric test, t-test, parametric test. Normally, this is homogeneity of variance, on at least intervals level, that is, must be number, then independence. Yeah, I think I've explained all these things before. If you have questions. So we have, so what we mean that this condition must be fulfilled before you can say, okay, I'm doing this. At least most important one must be number one. Even though the other two are not there, those the most important one, number one and number two. So the t-test family now, one sample t-test, independent sample t-test, pair sample t-test. If you have question, you can raise hand or chat. One sample t-test. Use the formula. T by x minus mu over standard error. And you know standard error is standard deviation over square root of sample. So S bar is sample mean. Mu 0 is target value of population mean. S sample standard deviation, N number of test sample. So when we say this one is one sample t-test, it's one group. You know, not the two groups you are comparing, but you are comparing one group with a particular mean in the population, which maybe the work has been done before. They've already known the mean. They are published. So that is the known, or I call it theoretical value. That is value that is in population. People just feel that's the real value because that was the available value they have. The previous works have been done. That's what they believe the value. Maybe we are talking of weight. Every weight in Abuja, of adult in Abuja, be 75. That's what we know. We have always known. So you now have your own group. You now see 600 people. Measure their weight. You want to compare the weight with the average, you know. Because if they say average 75, you may do your own, it may not be exactly 75. Maybe less, it will be higher. So you want to compare that your new one with the mu u, which is population. That's why, because you have only one sample, that's what they call it. Sample size, one sample t-test rather. Now, any question? So let's run that first one now. One sample t-test. There's a question. The following is the age distribution of 20 victims of a disease during an outbreak in the country. The age was recorded in year. These are the ages, 20 of them. If the victim in a neighboring country, if the average age of the victim, yes, if the mean age of the victim in a neighboring country was 33 years, can we say that the mean age of affected victim is the same in the two countries? So you see, the data file victim. I think I call it victim of disease. Hope is there, or Ebola victim. You see, somebody should share the data file. Ebola victim is there. Ebola victim. So that data set is there. If you have question, let me know, but somebody should share.
Yes, I should.
Yeah, you want to share? Is it a question?
No, sir, I want to share.
Okay, share. Yeah, it's the Ebola victim.
So can you see it?
Yes, you can see it. Yeah.
Okay.
Yes, you can see him. You can see serial number. You can see age. 20 of them you see. Then you can see those other one says die or not alive. Leave that one. That one were put there for some analysis or regression, but which is not for this particular. So it's only the age we are using. So as you can see, it's only one group. There's nothing like there's no group variable that divided into two or whatever. So go to see, go to analyze. You see, compare means. One sample t-test. Can you see? There. That's second option. No, you have to move along that something. Okay. Okay, you have done it. One sample t-test. So just move age to that place. So you now press, you see test value down. Where they put 0, put 33. You know, they say the other one is 33. The mean age of the other country is 33. You know, here now, it will calculate, you know, the mean age for this group now. You know, you have the data set, but the mean age for that other country, you put it there. That is the test value. So you now click OK. Okay, click OK.
Okay, sir.
Yes, you can see the result. Scroll down. Let's see what she have done down. You can enlarge your screen now. You can enlarge it. You are not done that because well, I thought you were bigger than that. Now you will see the first table will give you the n is total 20. There are 20 of them. It gives you the mean of those 20 people, which is 39.55. It gives you the standard deviation also. Now you see T is 2.287. 2.287. Degree of freedom is 19. You know that the degree of freedom is n minus 1 because there are 20 of them. So n minus 1, 19. The level of significance, or the p-value, that's sig, 2t, is 0.029. It shows that it's significant. Now, we have confidence interval of the difference. The mean difference is 6.550. You know, if you remember 33, this one is 39.55. You know that the difference is 6.55. Now, there's something I've not, you can see now that with hypothesis testing, T, there's a significant difference. But that difference between that group, the age group, or the age of those victims, and those of the people in the other neighboring country, which is 6.550, there's something we still have about them. We have the 95% confidence interval. Now, there's something I've not told you, not that I've not told you. You know, all this from, we started with chi-square 2 days ago. Is it day two of our lecture, the last two lectures, talk about chi-square. We just talk, okay, after the chi-square, you just say, okay, this is p-value, significant, non-significant. But we didn't talk about confidence interval. You know, there are two hypothesis inferential methods, as I told you, that we commonly use: confidence interval and hypothesis testing. What we have done now is hypothesis testing. We have also done something, confidence interval. I have already told you that confidence interval give more information than hypothesis than p-value. Because when you say hypothesis testing, we talk about p, because p-value is the end point of hypothesis testing. I said that p-value will tell you if it's significant or not. Yes, if there's significant difference between the two groups. The confidence interval will tell you if there's difference also. If there's significant difference, if it's statistically significant, it will give you the value of the difference. It will also give you the range of value within which you can find the population. So let's see it now. On this table now, this second table, 1 time t test you see here, there are two inferential methods. That t, degree of freedom, are significant. Those are tests. That means different, lower, upper confidence, that is confidence interval. Can you see now? So let's see. For hypothesis tests, we have already know that it's significant, because that's the only thing it tells you. From the p-value of 0.029. So we already know that t of 2.367, the degree of 19, degree of freedom of 19, is significant with that 0.029. Now, that is hypothesis test p-value. Let's look at confidence interval. Those three information we say confidence interval provide. We say that it will tell you if it's statistically significant also. How do we do that? It will tell you the difference. That one, you can see, that difference is 6.550. You have known the difference you are looking for. Then we tell you the range of value within which you can find the population value, which is the confidence interval, 76 to 1230, 12.34. Can you see that? So out of the three information that we have gotten to, one, the difference, which is 6.550, then the confidence, the range of value within which you can find the population value. So the range of value is 76 to, is it 76?
Is that point? It's 0.76.
Sorry, is it 0.76 rather?
Yes, 0.76.
0.76. That's why I say you should enlarge this thing. So 0.76.
Now let me enlarge it.
Now you now.
I don't know why it's not enlarging it. Why is this showing like this?
Okay, no worry, don't worry. Better small.
Is it?
It's better. Yeah. So 0.76 to 12.34. Now, what of the third one, which is how do you know if it's significant or not? And that's the only information p-value give you. This one give you 3, which we have already found out 2 out of the 3. That third one, without p-value, how do you know if this confidence interval is significant? Now, if you remember, no hypothesis say there's no difference. If there's no difference, what will happen? It will be equal on both sides. You minus 1 from the other, give it 0.
Yes.
That is, if there's no difference, that means that this difference is 0. Now, this confidence interval, this which give you a range of value within which you can find the population value. Look at the range. If it includes 0, that shows that it's not significant. So this range now, does it capture 0? It does not capture 0. What I mean by this is that if you, I don't know, you can stop sharing, because I don't know if I have anything to explain. Stop sharing. Let me share my slide.
Okay, sir.
Thank you. You know, I just jumped to go and measure it because even though here I've already calculated, can you see? We use hand to calculate. How you use hand to calculate the same thing, and hand to solve this to case of exam. Come out in exam. This is a way you solve it. No, subject x minus, you calculate the average. No, you add everything together, you divide by the total, you calculate the average. You now remove the average from each value. So your x minus x bar. You now square x minus x bar. You know, so that's how you calculate your variance and calculate your standard, so that you can get your standard deviation you use in the formula. Now, okay.
Prof, I have a question.
Okay, ask your question.
On the output that is having like one sample effect sizes, where we're talking about standardizer. I'm seeing standardizer, point estimate, not on the one you're showing on your screen. The output.
Okay.
Yes.
Okay. Okay.
The one sample effect sizes.
One sample effect size. And
yeah, one sample.
And just pointing effect size. It's just pointing, actually talking about that difference. We'll talk about that. I just want to bring out, if you look at this in 0.6 to 12.35, it can show very well here now. What I just want you to know, I will answer your question. What I want you to know here is that normally, if you move, because 0.76 to 12.34 is a range of value. So in between, you can have 0.77, 0.78, 0.79, up to 9 point something, 8 point something, up to 11 point something, up to 12.34. It can be any value. You will see from that 0.76 to 12.34, 0 is no one of the value. It cannot be. Does it make sense? So if this one is significant because the interval does not include 0. If the interval includes 0, then it is not. Let me just draw something. I'm trying to get this drawing. So okay. Okay. What I would say, let me put it here. Imagine you have a scale like this, and you remember Cartesian scale, where you have 0 at the origin. When you have 0 here, you can have 1, 2, 3, and good like that. You have -1, -2, -3. If something range from here to here, and something range from here to here, and something range from here to here. If somebody code that the confidence interval is from -3 to -1.5 here. The range of value, does it include 0? If somebody say from -1.3 to 1. As somebody say, from 2.1 to 4. Which one includes 0? Which one do not include 0 in the range of value? Remember, this is minus. This is minus.
The one from -1 to 1.
This is minus 2.
Minus 1.
1. This is minus 1.5.
5.
No, I would have done this thing before. This is from minus
1.3. 1.3.
1.1 and 1.3 to 1 here. This is 2.1 to 4. So which one includes 0? Which one does not include 0 in the ratio of value?
The minus 1.3 to 1.
Yeah,
includes 0.
Includes, thank you. So when you see confidence interval that start from minus something and end with something plus, that should I tell you that in the population, the range possible value for that thing, it can be any value in between minus that thing to plus the other number. That's why you know that 0 is one of the possible value, because 0 is captured among the possible value. So when you now see whatever the difference you have found, even if they say is the difference 2, but in as much, or they say the difference is 1 point something, in as much that it vary, it has captured minus, the confidence interval has captured 0. Sorry, is 0 in its range. It's not significant because it can be 0. And we know that when it is 0, there's no difference. I don't know if you understand me now. So, but this first, the first and the last, they are significant. The only difference is that here from minus to minus, here from plus to plus. So this from minus to minus to plus to plus, it means the same thing. Is it why the difference is that when you get minus to minus, what it means that, or let's say when you get plus to plus, because the difference you got is plus. So what it means is that when you are, when you are running your analysis, you select how you this minus this. It means that you remove smaller number from bigger number to give you plus. If you remove bigger number from smaller number, it gives you minus. So it doesn't really matter. But whether you remove bigger number from smaller number that give you plus or negative or whatever, if the difference includes 0, it means not significant. So I will explain further better when we do independent sample team. So sometimes that's why sometimes I usually run that independent sample team, because of it's easier to explain this different issue. But logically, it makes more sense when you are running it. See, let's talk about one sample T. Even sometimes also, if I would talk about, I will not even talk about confidence interval until I get there. So let's run that one. I can explain it further. Any question? Then your question, share what you said. Share your screen again. Yes. Question?
So here. This value.
Yeah. So, okay. So ask your question. Ask your question. Okay.
So this value here.
We have not even reached that. This one are different things. They are different things. So is when we say standardized, sometimes you see current D, ages direction. So it's just like when you run a lot of it, just like when we run the chi-square the other time, there are many things that are there that you may not actually make any sense to you when you are discussing. When you see something standardized, it gives you what the value should be in the population. You know, standardized means if we just like when we say standard, when we say standard normal distribution, standardized normal distribution. So when we saw the point estimate, the point estimate is the what you get exactly. Now you see now this value here is if you look at the lower limit of the 0.65, this one I can't see, is it 5, is it point something or 520? Thank you.
Please point, that's for point 529.
I can't even see it very well. So we discover that one is not even relevant here now. That one is your current D. So it's just this second table I just wanted to look at. So now this one now, without p-value, you can say this one is significant without including p-value. So using this confidence interval. That's what I wanted you to see there. So stop sharing. Let's go to the next one. Any other question?
Yes, sir. So just to reconfirm, you said level of significance. So if it is ranging between -2 to 1, where it involves 0, it then means that it's not significant. Is that what you said?
Yes. Don't worry. When we do the independent test, it will be clear up to you. You say the same thing. It will be clearer. Yes. Let's move to the next one. Independent t-test now. So otherwise known as independent measure t-test or independent sample t-test or simply student t-test. When you say student t-test, this is what you usually mean. Because the person that invented t-test usually use it for 2 independent group before intelligent people also, other intelligent people also. That's you can even use for one sample for pair. So it's the independent t-test they call t-test, student t-test rather. That was what Gosset published. It is used when there are 2 experimental conditions and different participants were assigned to each, or there's 1 experimental group and 1 group control group, or comparing means of 2 groups in an observational study. So here now, study design comes to play. Whether you are doing experimental or observational, you are comparing means of 2 independent groups. This question is, the tables below show the number of days lost to absenteeism per month over 15 months due to sickness in the mining and construction industry. Can we say that the mean number of days lost differ in the industry? Can we say that? So if we want to compare the mean day loss, so the sample size for each is 15. So we can compute it, look at it, using hand to compute. For the mining, you list the number, the X1, you list the number of days, add together, calculate the average, 5.8. For construction, if you calculate, the average is 3.73. So, you know, it's easy to calculate the average. Just add the value and calculate the average. All these other one is because you want to calculate the standard deviation. That's why you have to now remove the average from each value. Can you see? And now square it, because you know that if you remove the average from each value, is x minus x bar. If you, some will be negative, some will be positive, because those ones that are higher than the mean will be positive. The ones that are lower than the mean will be negative if you remove bigger value from it. The ones that are equal to the mean will give you 0. So we have negative, positive. If you try to add them together, it give you 0. So when you square them, x minus s bar square, you'll be able to get your sigma x minus s bar, that's the addition square. So you calculate your variance through that. When you calculate your variance, square root of variance standard deviation. So that's what you just did for each of them. So it's a rigorous one now. In the, if you have to do it, well, in exam, that's what we do. We give it to you to do. We give it to you to solve. Now, okay, before we show up, let's go and run it now. They lost to asceticism. Who will share it apart from Mercy? Apart from Mercy, who will share? Nobody? Abbas? Asmau? Farouk?
Sir? Yes, sir. I'll share, sir.
Okay, that's fine. Farouk, you are not there.
I'm here, sir.
So after Abbas, you are going to share. After Asmau, you are going to share.
Sir, I'm using my phone.
Oh. Imagine I'm using my phone now. How do we?
So I have connectivity issue with my laptop.
Yeah, you have even shared before. So this is narrow. Help us enlarge it. It's not in line. And you are in variable view. Go to data view now. Let's even see what is there. Click on data view. Thank you. You see, you know, when we talk about independent group, you have to arrange them in series. Can you see now? Series means that must be, if you look at it, the day loss is day loss. Can you see the value? But how do you arrange them? You know, we have two groups, mining and construction. So the mining, the first we put there, we label it. If you remove that label now, it's 1. Say 1, the other one 2. If you want to know, go to view, click on view. Click on view. Click on that, uncheck that value label, uncheck it. No, is it value label? Okay, that's fine. Wait. You see that it has changed to 1 and 2 instead of writing mining and construction. Can you see now? So we labeled, you have to now have a group variable, which is that differentiate the two. That's why we have this group variable. 1 mean mining, 2 mean construction. Is this group variable you're going to use to, you know, when you are entering, it's telling you how you enter your data. So it's this group variable that will tell you how you are going to, it will be required when you want to run the independent sample data, because there are two groups. So this one, serial number, is just a serial number for us to count very well that there are 30, 15, 15. Now, go to analyze. Go to compare means. Independent sample T. Now, you now move day lost. That's the variable you are testing. Day lost, move it, day lost. And you see group variables. That is what different. You now put that group, the one we say group, move it there. Immediately you move it there, it will say, it highlight. You see, you say question mark, that is, what are those groups? Click on that define group, the button below it. Group 1, put 1. That's my name. Put 1 because we label it as 1. Type 1 there now. And the other one, type 2. Know that. So that's why if you have, maybe you didn't use label 1, okay, you have to know what to type exactly. Is it urban rural? You have to go and type it. That's why it's better you code it so that it's easy. Okay. Immediately you do that, you can put in those question marks, say 1 and 2. Click OK. So show us go to the view. Try to go, maybe you can see it from there. Go to the result view. Go to window. Let's see if it will open it for us. Go to window to show us the result view. Window before that help. Beside help. On the SPSS icon, up. Window. Click on it. You see the output view. That output 1, that's 1, that first one. That's the that's viewer window, yes. Okay, stop sharing. This is slow. Stop sharing and share with us. If you stop sharing and not share the results. Because we are only seeing the data editor window, we didn't see the result. Enlarge your view. Enlarge your view. Thank you. Does not enlarge you. Thank you. You see the first table. It gives us mean. It gives you the the sample size. Give you group, mining, construction, 50-15. Mean 5.80, 3.73. The way we got it. It gives you the standard deviation. It gives you standard error. Then you now come to the bigger table. You will see the first you see is 11 tests. 11 tests for equality of variance. First of all, we talk about homogeneity of variance. You use what we call F-test to do it. Now, the significant, the p-value for that one is 0.670. It's not significant. It means that there's no heterogeneity. There's no difference in their variance. If you look at the standard deviation for both, they're very close, 2.04 to 2.086. They're very close. The same thing with the standard error. The same. It means that the two groups, the variability is the same, though the means are different, and that's the requirement. You need the same variability for you to use t-test. Now, so we now move. You also see, apart from you see equal variance assume, equal variance not assume. The value, if the way we have found out that yes, there is no there's homogeneity of variance, that shows that we have assumed equal variance. But if you see that it's not different, you can assume on equal variance. Look at T. T is 2.742. And that's what in calculation, that's what we get. And the degree of freedom is 28. You know the degree of freedom for this one because there are two groups. Is N1 minus 1 plus N2 minus 2, N minus 1. Or you say N1 plus N2 minus 2. So N1 plus N2 there is 30 because 50, 15, make it 30 minus 2, 28. Or you say N1 minus 1, which is 50.1, 50 minus 1, make it 14. The other one 15 minus 1, make it 14, 40 plus 28. Whichever way, the degree of freedom is 28. The significant, can you see 0.011? It's very significant. Now, that's the end of hypothesis test. Then the rest is confidence interval. You will see that what is the mean difference? 2.067. If you go and even remove, use your hand to remove 3.73 from 5.8, it gives you that 2.067. Look at the confidence interval. It's from where? It ranges from what to where? Can't see this thing. Is it 0.57? Where's your this thing?
0.532
to 3.
232 3.611.
Okay, the different mean different there. Then if you look at it, where it does not call, does it include 0?
No,
It's
it
just point.
starts from 0.53523. So it doesn't include
Yeah, for it to include 0, it has to start from minus and end with plus. If let's say the lower is minus something, and the other one doesn't have minus, you know that it has included 0. Okay, now, well, you can rerun this analysis. It will still be significant. It will not include 0, yes, but it will give you from minus to minus. So if you remember, when we were selecting, I say group 1 should put 1. 1 is mining, and you know that the mean for mining is 5.8. 2 is the second one you now put. 2 is construction. The mean for construction is 3.73. So if you remove 3.73 from 5.8, 5.8 is more than 3.73. That's why the value, the difference is positive. Now, as now go back now, just click on analyze. I want to swap it. I want to put that group 2 first. So go to analyze. You see what it will give you. Go to the same place. Compare means independent. Just click on that group. Click on that group. That group 1, 2, and click on it. And now click on that define, yes. Change that first one to 2 and the other one to 1. No be 12 for 2. Thank you. Yeah, okay, click OK. So you are removing group 1 from group 2 now. So the results, scroll down, you see every other thing. The t-test, the 11 test, everything the same. P-value the same. But when it comes to the difference, you now see minus, because you've just removed bigger value from the smaller value. You will see the confidence interval rate from minus to minus. It's still significant because that range does not capture 0. Does it make sense now? When you run your teeth, it gives you like this, minus to minus. Well, for experienced people, you just know. You just remove. But if you want to, it's confusing you, go back, change the sequence. It means that one that is serving as your group 1 that you put first has lower mean than the second one. That's what I give you. So you go and put the one that have higher mean first. If you even run their mean, you'll be able to see. You'll be able to know, okay, when you are doing it, you put the other one, the one that have higher mean first. It will give you positive. You get it now? But if you look at it very well, it just swap that, you see the all the standard error is still the same. You see, before it was 0.523 to 3.611. Can you see now? So now it just changed the same thing. Minus 3.611 to minus 0.523. So does it make sense? Any question? Any question?
Yes, sir, I have a question.
Okay, what's the question?
But sir, still after we change group 1 to 2, 2 to 1, the 0 is still not inclusive within the range from the lower limit and the upper limit.
Yes, now.
So why the change?
Huh? Why the change? There's nothing that changed, nothing changed. That's so that you have not gotten the logic, and it's good to get the logic. Nothing has
I
changed.
thought we are changing it to confirm the null hypothesis, like to get 0, but still.
No, we are not changing anything to get 0. I'm just telling you that, when I gave you the I gave you 3 scenarios on my own slide. I draw 3 something. When the range is from minus to minus is significant because it has not included 0. That's what we have demonstrated this last one. When the range is from minus to plus, it means that for you to cross from minus to plus, you must pass through 0. So that shows 0 is included in the range. That is the situation that is not significant. The other option is from plus to plus, which was when we first run this, it was like that. And I said the difference between from plus to plus and from minus to minus is whether when you were running analysis, you put the bigger one before the smaller one or the smaller one before the bigger one. That's what will give you either plus to plus or minus to minus. So, but in a situation, even if you put the bigger one, a smaller one before the bigger one, that it will give you mean minus 2 on something. If it's not going to be significant, the standard, the confidence level will range from minus to plus. Do you get it now? So maybe
Yes,
I will even look for a particular example. Is it clear now?
Yes, sir. Thank you, sir. Also, sir, how did we label construction for 1 and mining for 2?
What is it?
How did we label construction for 1?
How did we label it?
Construction for 1 and mining for 2, yes.
And that's Mukhtar, right?
Yes, sir.
Can you share? Let Asma stop sharing. Can you share your own?
Okay, sir.
Asma stop sharing so that sometimes if you won't click in it, they make more sense. They lost, yes, to sickness. That's it. Click on it now. You have not clicked, yes. You have to reshare. So you see, when you when you are having two independent groups, you have 30, for example, now you have 30 people. This one now is not people, but it's month, and 15 months for one group, 15 months for the other group. So since there are two independent groups, you have to label them. You have to enter the value on the same line. So it's still the same day to loss, all of them. Then you have to label one first. You have to first of all, so in this case, now we just enter mining from number 1 to 15. We now enter the value for construction from 60 to 30. Then how do we differentiate mining, the value from mining from that construction? There must be a variable. For some people, you can type it there and type mining construction, no problem. But the problem with that is that when you
So I can't really hear you.
if you now come to
Okay.
if you now come to when you are running the t-test, when they ask you for group, say group, you have to type the same thing there. No, you can make mistake. Why be typing mining construction? So, but from day one, when you are entering it, you use number to represent it. Though you can decide to call M for mining and construction C when you are entering. Just say instead of just put mining M for all of them. The other one, just instead of putting construction C. That's good, but it's good to use number. We enter 1 here. We now enter, that's for mining. We enter 2 for construction. So, but we label it. Go to your go to your variable view to see how we label it. Variable view. Now, where did you go now?
It's variable view.
Go up. Scroll up. You are variable view. Scroll up. You are high. We cannot see it. Okay, see my this thing that is covering it. Come.
So we can see it.
Yes, I can see it now. So you will see group. The group variable. Look at the label, value label. No, we have said because we put it's numeric. If you didn't put numeric, you cannot. Though if you put it's numeric, that's why you put number. That's why we call it numeric. We now say okay, this thing that is non-numerical variable, general natural, you are not putting number. What is the value? What does it mean? Click on that mining, that value label, that mining sound. Click on it here. Click very well now. I don't know. Click on that box in front. Can you see now? You see 1 is equal to mining. That's why we put 1 label mining, 2 label construction. That's okay. So that's why mining is labeled as 1 is labeled as mining, 2 construction. Are we together? Go back to your this thing. You can okay.
Yes,
You can come out. You can come out. You can cool okay. And go to your data view. So if you go to is it view also? Go to view and check that value. Go to view. Check value label. Check it. There's a value label. That is, check it. Click on it. Can you see now? It put, so you want to show me, I don't like it. It made the data to be too wordy, cloudy, too much. That's why I don't like it like that. But if you want to check, so, but if you don't like it, you just go to the view and off that thing. It's the number that will be there. But what the number means is what you are seeing, mining. So what the question you ask is what you do in data entry. That's what you should do.
Yeah. Okay.
So that one is gone, right? So you can stop sharing. Let's do the last one. Somebody shouted. I'm not hearing you, sir. Okay. You can hear me now.
Yes, it was that time.
Okay.
It was that time. I'm not really hearing you. Yes.
Okay. Is it Dr. Miller? It's Dr. Miller that shouted now, but it's not Dr. Miller that talk.
Yes, sir. Yeah, I was not hearing you.
I know what I'm saying. When I saw your shout now, somebody now say it was that time. I think it was you that shouted. It's another person that is talking. You get it now. Now, let's go to the last one, pair sample team. So, example, pair sample t, otherwise known as match pair t-test or dependent t-test. Can you see? The other one is the one we just finished now, independent sample t-test. Independent samples mean there are two samples, independent samples. But this one now, dependent t-test. Dependent is the same thing as paired or match. So in what situation do we use it? It is used when there are two experimental conditions and the same participant took part in both. That is, maybe those are different scenarios you can use for. For example, now you give some people a drug for sleep. People that cannot sleep, insomnia, a particular drug. You now come and ask them question. Maybe there's something you measure, maybe their headache or whatever. There's something you measure, maybe their blood pressure. Or let's say blood pressure drug, whatever type of drug you give them. You now measure. So the same set of people will now give them another drug. Apart from this first one, you now measure again. If you look at it, both what you are measuring, maybe their blood pressure or whatever, is the same group of people. That's what they call two experimental conditions at the same participant took part in both. Now, or you are comparing means of measure taken before and after an intervention or experiment. Maybe you measure somebody blood pressure before, or you measure somebody blood sugar before, or hemoglobin concentration before, and after you are giving your drug or treatment, whatever, after a while, all of them, you the same people. If they are 300, all of them must come by. It's the same people, not that you sample and that, the same people you give them after. You compare the measurement before and after. Or comparing means of the repeated measure taken from the same group in observational study. Like, for example, measure your blood pressure sitting and standing. It's not an experimental condition, but you take two measurements, similar measurement, two measurements from the same group of people on two occasions. Or comparing means of peer observation, measurement from right and left eyes, here, corresponding teeth, identical twin, the right and left breast. Think of anything that appear naturally as peer in the body. You can use it also. Of course, it's from the same people. This one is not a matter of you are not taking measure before and after now. is from the same people, where you take the measurement of the two organs that are opposite each other, right ear, left ear, right eye, left ear, all those things. Those are the things you use peer t-test for. Now, look at this example. The table below shows anxiety score before and after counseling of 9 persons prior to disclosing to them their HIV status. Did the counseling significantly influence their anxiety score? Look at it. The first, you have serial number, there are 9 of them. Before counseling. Look at the score. Score after counseling. You see, if you scan through, you see that before counseling, averagely is like they are higher. After counseling, averagely they are lower. But it doesn't look at number 4 person. The thing is higher after counseling. So it doesn't have to be, maybe it's lower or whatever. I think that's whichever way. You now come, what you now do is that you now look for the difference. Because this one, you are looking at you want to calculate the mean of the difference. For each of the person, you take the measurement after from before, you remove it, give you D different. Some, if this the difference may be positive, some may be 0, some may be negative, you get it. You now add the difference. You now calculate the average of the difference, the mean of the difference. The sigma difference here is 300. So you are not interested in adding the total or whatever. It doesn't really make sense here. Though the computer, in calculating it, it doesn't make sense. You don't need to get, but when you are running it, the computer will give you the mean for each of them. But actually, in calculating it with hand, you don't need that. The difference is the one you do the total, calculate the mean. The mean of the difference is 3.3. You know that in the formula for the standard for the pair T is bar D, the mean of the difference, bar D over standard error. And the standard error is standard deviation of the difference over square root of sample size. Can you see? So in the formula now, bar D is there, standard deviation of that difference is there, and square root of, you already know the sample size is 9. So the standard deviation, for you to calculate the standard deviation, and that's why you have to do all this work. D minus bar D, you look for the difference of each of the difference from the mean of the difference. Can you see now? Then you now square it. You know that naturally if you had it, it will be 0. You now square it. After square, you now calculate, you now get the summation. You now calculate the standard deviation. Now, okay, I think it's calculated here. Everything calculated here. When you do that now, can you see? So pair T will be D by D over standard deviation of this over this. If you look at it, it gives you 4.362. Now, let's run it. So let somebody, okay. Yeah, I think we have discussed that. Okay, let somebody share. Who will share now? The person that promised to share. Who was the person that, is it Yaro that promised to share? Farouk. Farouk, okay, you have shared now, Abi?
No, sir, it's not me. I said I'm not using my system. I have connectivity issue.
Okay, who will share?
So I can share.
Okay.
Can you see it, sir?
Yeah. You know, some people are naturally stingy, they cannot even share anything. even to share their view. Can you see? I want you to see the difference between the way you enter independent T and pair T. For the one sample T, there's no problem because it's only one group. The independent T will really say the two groups, you arrange them in series. That's why you have to have a variable that will differentiate them. The one we have just done now, that we have to have a variable called group. Where you now say group 1, group 2. But this one, because even though we have two sets of the reading, they are from the same people. So it's from number 1, it's the same person, 1 to 9. The only thing is that the first DBP counseling before anxiety before score before counseling, SBC. For each of them you put. The next one is score after counseling you put. So if you look at, if number 1 is Eunice, this before 121 will be for Eunice. 76 Eunice will be there. If number 2 is Felix, the 2 reading must be for Felix. Not like and so that's why I call pair for each. So because what you are removing from one is the reading from each person. So this is what we call parallel. You enter it in parallel. But the other one, you enter it in series. You finish entering one, you continue that series. But here now you enter it, you enter in front of it, parallel. Can you see now? So click on analyze. So go to compare means. You see pair, here sample t-test. And you see the way it comes here. So under pair 1 now, they just assume that you may even know many to be the only one we have here. So score before, it depends on the one you know is higher. Though it doesn't really matter, change the better, it makes sense. Score before canceling, generally higher. You move it first. Yeah, score before canceling, move it. Click on it. Move it. Then score after canceling, move it. It will move it in front of it. Can you see? If we have many variables like that, that's why we'll be moving them one to one at the same time. We're going down. Yeah, okay. Okay. Okay, now click OK. So let's see your this thing, your result. Great. You see, if you look at the first table, it shows you score before canceling, mean. No, I told you that you calculate, but if you actually using hand to calculate, you don't need it. You calculate that one. But computer will give it to you, their own mean score, the other one, their own mean score. But what you got there, come to the table. No, the last table. Come to the last table now. You will see mean of the difference. This with the difference. Can you see 33.33? Standard deviation of the difference. The standard error also. Then you now have confidence interval. Though the way this one arrange it, if you look at this one now, the T, degree of freedom, and p-value is the last one. It's not like the way a pair t-test arrange the way independent t-test arrange. The last 3 part is T, 4.362, degree of freedom, 8. You know, there are 9 of them, 9 minus 1, because it's only one group of people. So is in the group of the people now, the number The sample size is 9 people. 9 minus 1, 8. This is the p-value, is significant. Now, the confidence interval, is this significant or not? Is the confidence interval? Eh?
Confidence interval for the paired sample test.
Yes.
It's not, sir.
It's not?
Doesn't have 0, so it's significant.
Yeah. It doesn't have that. Well, who says? Somebody says it's not.
It's right. It's Asma would have said it's not.
I want that to explain.
I can't hear you.
I want that to explain. I want Asma to explain. Why is this? Why did you say it's not?
Sorry, sir. I was supposed to say it is because it doesn't have a 0.
So, great. That's just it. It's not because it doesn't have a 0. So that's just the summary of t-test now. Any question? Any question? Oh, no question. How many people? Only 7 of you. Apathy as 13. So thank you. If you don't have question. Tomorrow.
Thank you very much, sir.
Thank you very much, sir. We
T-test
really
now.
appreciate
Thank you very much, sir.
Welcome. Okay. So this t-test now, the non-parametric counterpart, we do them tomorrow. Thank you.